Hello and welcome to this lecture on Maxima and Minima by the method of Lagrange's multiplier. So if you remember, in the last lecture we did the maxima and minima for a function of two variables, and we also solved example where we have to find the extreme value of function subject to a constraint condition, that is the domain is bounded by a triangular region there. And to solve that, we calculated the critical points by substituting the boundary in the function. And but that method of substitution do not always go smoothly. Okay, and this is one of the reason that we are going to learn one more method here, which is the method of Lagrange multiplier. So first we'll just take one example to show that sometimes the substitution do not always go smooth. Okay, so that means we end up getting something that is not desired, and then we'll talk about this a more powerful method of Lagrange multipliers and how we can utilize this to find the extreme values of the functions having some constraint conditions. Okay. So let us first take one example, that find the points on the hyperbolic cylinder given by this equation that are closest to the origin. Okay, so first, if you look at the geometry of this hyperbolic cylinder, then you can see that this is the x-axis, y-axis, and z-axis, and this is the hyperbolic cylinder, which is given by this equation x square minus c square minus 1 equal to 0. Okay, and if you have to locate the point on this cylinder which is closest to origin, so you can see that here is the origin, and so the points which are closest to origin are this point here, which is 1 0 0, and on the other side this point which is minus 1 0 0. Okay, so one on this cylinder and one on this one. Okay, uh, now if we go with the method that we learned in the previous lecture, then first we have to find a point which is closest to origin. Okay, so that we have to minimize a function of distance from origin to some point on this cylinder. Okay, so by distance formula, distance will be root of x square plus y square plus z square. Okay, so we have to actually minimize the distance. Okay, and if distance is minimum, then the square of distance will also be minimum. Okay, so a simple function, this will be the function for the distance square that we are going to minimize. Okay, so x square plus y square plus z square is the function, and it is subject to the constraint that the point xyz is on the uh, cylinder, okay, hyperbolic cylinder. So the method, if you remember, says that we can if we substitute one of the variable from here, this condition here, okay, and then it will be a function of two variables, and then we can uh, find the critical value, and then we can see whether it is maximizing or minimizing by the derivative test. Okay, so if say I consider here that x and y to be the independent variable and z to be the dependent variable, so I can substitute z square as x square minus 1 here, so it will be a function of two variables x and y. Okay, so that's what I said, that if we regard x and y as independent variables, okay, so z square will be x square minus 1, and so this function can be written as a function of two variables, 2x square plus y square minus 1. Okay, and so if we have to now maximize or minimize this function, then by method what we have to do is differentiate this with x, differentiate this with y. Okay, so find the two partial derivatives and put them simultaneously equal to 0 to find the critical points. Okay, so h derivative x, from here you see it is 4 times x, and h derivative y is 2 times y, and so if I put them equal to 0 simultaneously, that it gives me the value the point as 0 0 x0 and y0. Okay, but you see that x0 y0 points are not lying on this uh, hyperbolic cylinder. Okay, so okay, this is not possible. So what actually went wrong here? Okay, so what went wrong is that this function hxy, which we are trying to find the critical points, the domain of this is the complete xy plane. Okay, but so method gives the right point based on this function which has a complete xy plane as the domain, but we only want those points which are actually on the cylinder. Okay, so what happened was that the first derivative test found, as it should have, the points in the domain of h. Okay, where h has a minimum value, and this function h has the domain of complete xy plane. But on the other hand, we want the points on the cylinder where h has a minimum value. Okay, and uh, the domain of this cylinder is either on this side or in this side. The points which lie between in this band of 1 and -1 are not in the domain of the cylinder. Okay, so 0 0 from here it is calculated correct, but actually we don't want that point. We want points on the domain of the cylinder, okay, which is outside this band of -1 to 1 of the value of x. Okay, so uh, although the domain of H is the entire xy plane, the domain from which you can select the first two coordinates of the xyz, that is the value of xy, on the shadow on the cylinder is restricted to the shadow of the cylinder on the xy plane, and it does not include the band between -1 and 1. Okay, so how we could have solved this? If we have to solve this by the same method of substitution of the constraint condition in the function and then use the critical point, then uh, instead of treating xy as independent and z as dependent like we did, instead of this, if we have chosen y and z as uh, independent and x as the dependent variable, then we might have got the answer. Okay, so you can try that. If you treat x as the dependent variable, so we can take x square as 1 plus z square, substitute it in the f function, and then it will be a function of two variables y and z, and then you calculate the y derivative, z derivative, put that simultaneously equal to 0 and solve that, then you will get the accurate answer. Okay, because on the yz plane, this uh, hyperbolic cylinder, on the yz plane, if we take its projection, then the whole yz plane is uh, will become the domain. Okay, if y and z are independent variable, so it will solve our problem. Okay, so the another way by which we can solve this is the method of Lagrangian multiplier. So let us first solve this example, and then I will explain what exactly is the method. So another way to find the points on the cylinder closest to the origin is to imagine a small sphere centered at origin expanding like a soap bubble until it just touches the hyperbolic cylinder. Okay, and at each point of contact, the cylinder and sphere have the same tangent plane and the normal line. Okay, so at the point of contact where the sphere and cylinder will meet, they will have the same tangent plane here, and they will have the same normal line, or you can say the normal lines are just multiple of each other. Okay, so if the sphere and cylinder are represented as the level surfaces at w0 of the functions, this f and g. Okay, so at w0, that means f0, this will be just this level surface will be this sphere, and when w0 means g0, then it will be x square minus z square minus 1 equal to 0, which is this hyperbolic cylinder. Okay, so the normals to surface will be the gradient f and gradient g. Okay, and by definition they are the same normal line, or they are parallel. Okay, so the gradient f and gradient g will be parallel where the surface is touch. Okay, so at the point of contact of these two surfaces, the gradient to the function and the gradient to this second function, they will be parallel. And if it is so, then there should exist some scalar, say lambda, such that the gradient of f is equal to this lambda times gradient of g. Okay, so if we solve this equation, because we have f function, we have g function, so we can calculate their gradients. Means uh, gradient here means the uh, x derivative in the ith direction plus y derivative in the jth direction plus the z derivative in the third direction. Okay, so by just writing f this and g this and the definition of del operator, that means the gradient. This is the del operator, I times x derivative plus j times y derivative plus k times z derivative, and I, j, k are the unit vectors in the direction of x, y and z, and this sign is for the partial derivative because function is of three variables now. And this is the f function, so its gradient of f equals lambda times this is the gradient of the g function. Okay, so del operator on g. Okay, and so we can take this derivative here, so I times x derivative of this function, and x derivative of this is 2 times x, so 2xi plus j times y derivative of this, so y derivative of this whole function is 2 times y, so 2yj plus k times z derivative of this, so which is 2 times z, so 2zk equals lambda times x derivative of this function, which is 2 times x. Okay, so 2xi plus j times y derivative of this, and there is no y here, so y derivative is 0, so there is no term of j, plus k times z derivative of this, which is minus of 2z. Okay, so minus 2zk. Okay, now for this to be equal, we can equate the coefficients of I, j and k on both sides. Okay, so what we get is 2x must be equal to lambda times 2 times x. Okay, the 2 times y must be 0 because there is no j here. Okay, 2y is 0, and 2 times z must be equal to minus 2z times lambda. Okay, so now we have three equations, four variables. Okay, uh, and now since x cannot be 0 because x0 is not the point on the hyperbolic cylinder. Okay, so x has to be non-zero, and if x is non-zero, so this first equation implies that lambda must be 1. Okay, and if lambda is 1, then this third equation immediately says that z must be 0. Okay, and second equation gives us y 0. Okay, so what we have is uh, x points which are non-zero with y 0, z 0 must be the points. Okay, so points are of the form x 0 0 with x is a non-zero value, and these points lie on the surface. Okay, so x square minus z square equal to 1 is the surface with z value 0 here, so we can immediately calculate x as plus minus 1. So what we get actually is the point plus minus 1 0 0. Okay, or that means 1 0 0 and minus 1 0 0 are the points on the cylinder which are closest to the origin. Okay, and that's what originally we saw through the geometry. Okay, so to solve this numerical, what we solved is the normal to function equals lambda times normal to the other function, and del f is lambda times del g, which resulted in three equations with four variables. Okay, so and but we had a constant condition which acts as a fourth equation. Okay, so we had actually four equations in four variables, so we solve them for x, y, z. Okay, to find those points x, y, z. Okay, so this is method of Lagrangian multiplier. okay, which says that suppose you have f function and g functions are differentiable, and the gradient of g is non-zero when g equals to 0 is the constraint condition, okay. And to find the local maxima and minima of value of function f subject to this constraint condition g is equal to 0, okay, if these exist, these local maximum minimum. uh, Find the value of x, y, z and lambda that simultaneously satisfy the equation that the normals are parallel and the constant condition, okay. So if you have to maximize a function f subject to a constant condition g, then what we have to do is we have to equate this equation, okay. That is the at the point of contact, the normal to the function which we have to maximize or minimize must be equal to lambda times the gradient on the g, okay, the normal to g, and this constant condition is already there. So these are actually four equations in four variables x, y, z and lambda, okay. So we can solve these equations to find these variables, and so x, y, z will become the points at which we can have the extreme values, okay. So some care must be used in applying this method, okay. So an extreme value actually may not exist. The condition this that the normals are parallel is a necessary condition for the occurrence of extreme value of the function, okay, subject to this condition, okay. But it does not guarantee that the one exists as this condition is not the sufficient condition for existence, okay. It is a necessary condition, but it is not a sufficient condition, okay. So it may give you points x, y, z, but then we have to visualize or see whether those points are actually the points of maxima or minima or not, okay. So let us take one more example here. Say find the greatest and smallest value that the function this fxy equal to xy takes on the ellipse this, okay. So we have a function f which we uh, have to find points and subject to constant condition that x square by 8 plus y square by 2 equal to 1, okay. So we want to find the extreme values of this function subject to this constraint condition, okay. So and this function is nothing but this ellipse, okay. So method of Lagrangian multiplier says that we have to find the values x, y and lambda for which the normal to this is parallel to normal to this, that means del f equals to lambda times del g, and together with the constant condition which is this, okay. And here functions are only in x, y, okay. So there is no z, so gradient will be uh, the I times x derivative plus y times j derivative, that's it, okay. So we can uh, calculate the gradient of this function, and gradient of this function means I times x derivative of this which is y, okay. So we get y times I plus j times y derivative of this, and y derivative of this is x, so we get plus of x times j. This is gradient f, okay, equals lambda times gradient g means x derivative of this which is 2x by 8, that means x by 4i, plus the y derivative of this which is 2y by 2, that means simply yj, okay. And this condition g equals 0, which is this function equal to 0, okay. So we have if you equate these both sides, so we'll get two equations from here, and third equation is this. We have three equations in three variables x, y and lambda, okay. So from here y will be equal to lambda x by 4 and x will be equal to lambda y, and this third equation is already there, okay. So what we have is these three equations, okay. And uh, then from the first two equations, if we put x as lambda y here, so it will be y is equal to 1 by 4 lambda square y, and so if you take this to other side, then either y is 0 or lambda is plus minus 2, okay. If y is 0, then from the second equation x will be also 0. Okay, so x and y will both be 0, but the point 0 0 is not on the ellipse. It is, this third equation is not satisfied for this point. Okay, so hence y cannot be 0, so this y equal to 0 is not possible. Okay, so lambda must be equal to plus minus 2. Okay, and if y is non-zero, okay, then this lambda must be equal to plus minus 2. And if lambda is 2, then x becomes 2y. Okay, if lambda is minus 2, then x becomes minus 2y. So x must become or x becomes plus minus 2y. Okay, so if we substitute x as this here, then we can solve this and find y values. Okay, so y must be plus minus 1, and if y is plus minus 1, then we again get what x is. Okay, so the function fxy equal to xy therefore takes on the extreme values uh, on the ellipse at 4 points. Okay, plus 2 1, minus 2 1, and plus 2 minus 1, and minus 2 minus 1. Okay, so with y value this we can calculate x, so x comma y points. Okay, the extreme values are xy equal to 2 and xy is minus 2. Okay, so function is xy, so with this we get either 2 or minus 2. So if you look at the ellipse and the function xy is equal to constant. Okay, so xy equal to constant are these curves. Okay, these curves touch the ellipse here or here, okay, or here or here, 4 points. Okay, and at these points the normal to ellipse and normal to this curve xy is equal to constant. For this particular point they are in the same direction, and gradient of f is 2 times gradient g. Okay, so lambda is 2 here for this case and also for this third case. Okay, for the second and fourth quadrant the lambda value is minus 2, the gradient of f is minus 2 times gradient of g. Okay, uh, the method can be extended when you have more constant conditions. Say for example, if you have two constant conditions, so many problems require us to find the extreme values of a differentiable function f whose variables are subject to two constraints, and if those constant conditions are say g1 equal to 0 and g2 equal to 0, and both g1 and g2 are differentiable with the gradient of g1 not parallel to gradient of g2. Okay, so if it is parallel to if the gradients are parallel, then it will reduce to a then one can be written as a multiple of other, that means del g1 can be written as a constant time del g2. Okay, so instead of a plane we will only get a line. Okay, so we find the constraint local maxima and minima of function f by introducing two Lagrangian multipliers lambda and mu, and then for any point p uh, where function takes on extreme values, that point p we can find by calculating the values of x, y, z, lambda and mu that simultaneously satisfy these three. Okay, one is this, that the gradient of f equals lambda times gradient g1 plus mu times gradient g2, and these two are the constant conditions. Okay, so these are actually if the function is of three variables, so this will give three equations, and these two equations, so total of five equations in five variables x, y, z, lambda and mu. Okay, and gradient g1 is not parallel to gradient g2. If it is parallel, then this del g1 can be written as a constant times this, so they can be combined to reduce these two constants into a single constant. Okay, so uh, we will have like five equations in four variables in that case. Okay, say we take uh, this example that the plane cuts the cylinder x square plus y square equal to 1 in an ellipse. Okay, find the points on the ellipse that lie closest to and farthest from the origin. Okay. So what we have is a cylinder, x square plus y square is equal to 1. Okay. So this is the equation of circle which is true for all z values. Okay. So it's a cylinder in the direction of z. Okay, with the center at origin, okay, and radius 1, and there is a plane which cuts this cylinder in an ellipse. Okay, so we have to find the points which are closest and farthest from origin. So again we have to maximize or minimize the distance function. So we are again choosing a square of the distance function. Okay, because uh, if the distance is point gives a minimum distance, the square will also give the minimum distance. Okay? And these are subject to two conditions, this g1 and g2. Okay? So geometrically what we have is this cylinder which is x square plus y square equal to 1, okay, for all z, and there is a plane which cuts it into this elliptical curve. Okay? So method says that if you have two constraint condition, then the normal to this must lie in the plane generated by the normals. Okay, so this gradient equation which says that the normal to this function at the point of contact must lie in the plane generated by the normal to this two g1 and g2. Okay, and subject to these two constant conditions. Okay, so gradient of f means the x derivative times I cap plus j times y derivative plus k times z derivative. Okay, so what we get is 2xi plus 2yj plus 2zk for gradient f equals lambda times gradient g1. Okay, so I times x derivative which is 2xi, j times y derivative, so 2yj, and there is no z here, so k times z derivative is 0. Okay, plus mu times x derivative is 1, so plus I plus j times y derivative which is again 1, and plus k times z derivative which is again 1. Okay, so we can combine these two to write ijk form, and then we can compare both sides to equate the coefficients of I, j and k. So 2x must be equal to 2 lambda x plus mu, 2y must be equal to 2 lambda y plus mu, and 2z must be equal to mu. Okay, so we get these three equations. So from here we can eliminate mu by substituting mu as 2z here. Okay, and then we can rewrite this by taking x on one side and from this equation y on one side. Okay, so we get this. So from here if either z0 and lambda 1 can satisfy this, or if lambda is 1 then z must be 0, that's one thing, and if lambda is not equal to 1 then we can calculate x as z over 1 minus lambda and y as z over minus 1 minus lambda. Okay, so and x equals y in that case. Okay, so what we have is if lambda equals 1 then z must be 0. Okay, so lambda 1 z 0 must satisfy this, or if lambda is not equal to 1 then x must be equal to y and both values are equal to z over 1 minus lambda. Okay, now the first case when z is 0, then if you solve the constraint conditions with z0, then first equation is x square plus y square equals to 1, and second is x plus y equals to 1. So these two will be satisfied only on for these 2 points 1 0 0 and 0 1 0. Okay, so that means these 2 points on the ellipse. Okay, on the other hand, if you have this x equals y is equal to z over 1 minus lambda and lambda not equal to 1, then because y equals x, so again I can substitute y equals x in these two equations. So the first will give equation in terms of x and other will be in x and z. Okay, so I can solve these two again. Okay, so for x equal to y, the constant conditions become this. Immediately I can solve first for x. Okay, and then I can substitute the value of x and solve this for z. Okay, right. So we can solve first for x. So x is plus minus root 2 by 2, and for each value of x we can solve this for z. Okay, and because x equals y, so y values are same as x. So what we get are 2 points, p1, which is where x and y are both positive and z is 1 minus root 2, and p2 where x and y are negative and z is 1 plus root 2. Okay, so this is a p1 point and this is a p2 point. Okay, so now we have got 4 points, 1 0 0 0 1 0, and this p1 and p2. Okay, so you can see that the point 1 0 0 and 0 1 0, they are the closest to origin, and the point P2 that we got here is the farthest from the origin, and we also got one point P1 which is neither closest nor farthest from the origin. Okay, but we got that point by this method. Okay, so that's why we have to be careful that whatever points we get from this method, we have to find out from the geometry or by calculating the values whether they are actually the extreme points or not. Okay, so this is it for today. From the next lecture we'll start with the uh, this lecture on sequence and its convergence. Okay, have a very good day.